Okay.
Good evening, everybody. You're all, as usual, very welcome this evening. And it's my pleasure to introduce you to Sam Lander from University of East Anglia. With no further ado from me tonight, I'm going to hand over to Sam. There will be time for questions, and they can go in the chat or in real time at the end. Sam, thank you.
Okay, so if I see something in the chat, should I just sort of try and pause and answer it as I go? Or?
Yeah, you can do exactly as you wish. We're pretty free and easy here.
Okay, I'm not sure if I can maximize this or if that will cause it. Maybe I'll leave it like this if that works for the rest of you.
Yep.
So you see the bits. It's not quite as pretty as full screen, but it's just
it should work full screen. We have been successful previously.
Okay, I'll try that. I won't see you lot, but yeah, in that case, I won't see any comments. But Paul, please feel free to interrupt me.
Yes.
Just
okay then.
Tell me out loud that there's something in the chat.
Sure.
Okay. Just maximize that. Okay, is that all still fine?
It is indeed.
Okay. Okay, so then thanks very much, Paul, and to everyone for turning up. And it's a privilege to give this talk to this national and in fact international collaboration. So obviously, I'll start by saying I don't know all of your backgrounds exactly. So if at some point I go too quickly over something, or even perhaps too slowly, please feel free to let me know, and also to interrupt. I think this should be within time. So I think there's plenty of time for questions whenever. So my talk is on magnetars and the dramatic lies. In a sense, magnetars are defined by being dramatic. So I'll explain that in a minute. So to start with, I want to give an overview of neutron stars in general. So magnetar is a class of neutron star. It's not the most well-known class, of course. So I'll present this talk in a sense chronologically. So I'll give some description about the history of radio pulsars, which was the first manifestation that we knew of neutron stars. Talk a little bit about neutron star theory and our understanding of what we observe, and why we're sure that radio pulsars really are neutron stars. Then I'll move on to magnetars in their original guise as high energy emitters, so X-rays and gamma rays. And then talk about this very recent discovery that at least some magnetars and possibly all at least some fast radio bursts and possibly all of them are powered by magnetars. So that's the central engine for these mysterious bursts. And then I'll wrap up with a bit of an outlook for magnetar observations and theory, and maybe what's on the horizon for us. So we celebrate 55 years now, very nearly, of radio pulsars. And so radio pulsars famously were discovered in 1967. In a sense, we were expecting them from the 1930s. So the neutron was discovered in 1932. And then a little bit later in 1934, Bader and Zwicky published a really far-sighted paper that suggested not only that there could be this object, neutron star, but then it's one thing to argue that something can exist in principle, but for astrophysics, you also want to know, where are you going to find this object? How can this hypothetical object come into existence? And they argued convincingly that these objects could form in supernovae. And indeed, that's where we get neutron stars from. So a star comes to the end of its life, nuclear fusion processes cease. The nuclear fusion is what gives the star the enormous pressure required to withstand gravity. So you have gravity acting inwards that wants to collapse this star, and you have a pressure that pushes outwards. At the end of the star's life, those fusion processes cease, and you get a collapse in the amount of pressure that you've got, and so gravity wins. So then the core is compressed into a neutron star for the right range of masses, at least, and the outer material is blown off in a supernova explosion. So the broad picture that Bader and Zwicky sketched back in 1934 is still about right. And then things went quiet. We had this proposal for where we would find a neutron star, what they would look like roughly, but we saw nothing. So neutron stars was really a bit of an esoteric area of research for 3 decades. Even though, as I'll describe a little bit in the next slide, many of the basic properties of neutron stars, you don't need to observe a neutron star to deduce those basic properties. It's essentially an application of the physics that we've devised and tested on Earth. And it's just taking those physical theories to the realm of where, in principle, a neutron star would be. And actually, you can get a long way with that without a single observation at all. So even before 1967, when we finally discovered radio pulsars, we knew in principle what their internal structure would be, lots of details about them. So then there was a few hints in the mid-60s of radio emission from the Crab Nebula and that kind of thing. But the discovery of pulsars famously was, so you can see in this, this red squiggly line on the top right there. So it was discovered famously by Jocelyn Bell, who was then a PhD student working under Anthony Hewish. And so she saw this through her radio detector. She saw this kind of what she called a bit of scruff. She got the detector to, she got the paper to spool through faster so that she could expand out what was going on in that signal, and saw these characteristic pulses. And they're a little bit variable from pulse to pulse, but integrated over a long time, these are enormously stable. And there were all sorts of suggestions to start with, even the idea these could be little green men or something. But the 2 less science fiction suggestions, well, no, 3 probably, were that they were either neutron stars, so the radio beam from the magnetic pole of a neutron star, or they were pulsating neutron stars, or they were white dwarfs. And then in the following couple of years, so for that very first pulsar, so from that radio pulse, measuring the gap between the pulses, and assuming it's because it's rotating, the object that produces this is rotating, you can measure the rotational period, and that's fast. That's of order a second or something. No normal star can rotate that fast. But for the very first neutron stars, you could just about get a white dwarf to rotate that fast. Then in 1960s, between 1967 and 69, I think maybe in 68 it was, they found a neutron radio pulsar where the period was a little bit shorter. And by that point, the white dwarfs are out of the question, because if you try to rotate a white dwarf with a period of much less than a second, it goes past what's called its breakup velocity. So the object becomes more and more oblate, and then eventually it loses mass around the equator. So you cannot, if you try to spin a white dwarf that fast, it just breaks up. So the only object left is a neutron star. And the basic picture, and perhaps the embarrassing thing is we haven't gone as far from that basic picture as we would like, is that you have, I can point with this, but you have a rotational axis which points vertically in this plot on the bottom right. Then you have a magnetic field axis, which is different from that rotational axis. The star rotates around its rotation axis, and then that magnetic pole sweeps across the universe, and if you're lucky, it sweeps past the Earth. And every time it sweeps past, if there's some mechanism for producing radio emission along that pole, every time it sweeps past the Earth, you get a pulse. So the bit of the story that's a bit unsatisfactory is pinning down exactly how that radio emission mechanism works is still under discussion, even more than 50 years later. It's a really difficult problem in electrodynamics. But broadly speaking, some picture like that has to work. One way or another, that radio beam is created and it sweeps past the Earth. So as I said, in a sense, we were waiting for neutron stars. And that's in contrast with the discovery of white dwarfs. So the discovery of white dwarfs really was revolutionary. So we found these know from the Hertzsprung-Russell diagram that a star which is a main sequence star which is faint is sort of reddish, and a main sequence star which is bright is bluish. And we found these blue but faint stars, which meant that the emitting region was very small, which meant they were much more compressed than a normal star. And this was a shock at this stage, and we needed to find. It wasn't clear these couldn't be powered by nuclear fusion. They're extremely dense. They're extremely small, so that the gravitational pull was very strong. So you needed a new source of pressure for the white dwarfs, and that was eventually we realized that had to be a kind of degeneracy pressure, it's called. So for white dwarfs, it's called electron degeneracy pressure, and that's the large scale effect of the fact that on small scales, electrons, neutrons, any other fermion, they don't want to be too close to each other in a sense. They can't, by the Pauli exclusion principle, they can't occupy the same quantum state. So that causes them to resist being compressed too much. Once that mechanism was understood for white dwarfs, it wasn't a big leap to say, well, if there's an electron degeneracy pressure that keeps white dwarfs up, there should be a neutron degeneracy pressure as well that would keep up this hypothetical object, the neutron star. So that was why once we'd found white dwarfs, which were indeed a shock, the neutron stars we were ready for them in a sense. So like I said, for all stars, you have the star as a balance of pressure pushing outwards against gravity pulling inwards. For a normal star, which is powered by fusion, you have a large object and the pressure is relatively weak. For a star where fusion has ceased, you might have a white dwarf, you might have a neutron star, but then if you pack matter any more tightly than that, you have no source of pressure left that can balance gravity. So at that point, you would get a collapse to a black hole. So in particular, if you have a mechanism for adding some more mass onto a neutron star, or if you have two neutron stars that in a binary orbit that inspiral and merge, the result of that then is a black hole. So neutron stars are in a sense the last frontier where you have matter. They're the densest possible star. And as I said before, the remarkable thing is all of those properties, the basic properties of a neutron star, you can predict them without knowing that the neutron star actually exists. So yeah, so all of this basic structure that I've sketched on this slide now. So as I said, a neutron star it's essentially a spherical object. It's a balance of degeneracy pressure against gravity, and it rotates about one axis, this rotational axis which I've labeled as omega here. But the magnetic field axis is generally different, and the radio beam, one way or another, we don't know the details, emerges in a way that's aligned with that magnetic axis. So that emission comes from the exterior region of the neutron star. And it's the typical magnetic field strength that you get for a neutron star is about 10 to the 12 Gauss. We don't measure it directly, but we can infer it from the fact that the star spins down over time. So the gap between those pulses very, very slowly increases. So that means the star is losing rotational energy. And we have a formula for how that works, which is related to the magnetic field strength. So once we see how the star is spinning down, we can, and its rotational period and the change of that rotational period in time, we can then take our formula, rearrange it, and we find out what the magnetic field strength must be to cause that particular spin down. So that's the exterior, and that we actually see. And then for the interior, this is all, so we have some hints about the interior from observations now, but essentially this comes from theory. So we have a core with predominantly neutrons, protons, and electrons, which are above nuclear density, so that this whole region is at higher density than atomic nucleus. And these form three liquids essentially. And then the surprising thing is, in the sense that the neutrons form a superfluid and the protons form a superconducting fluid. And there's nowhere else in the universe, as far as I'm aware, where you have such a large pool of superfluids and superconductors. These are, well, for superfluids on Earth, we only have liquid helium just above absolute zero. It becomes superfluid. And then for superconductors, we have superconductors, but they're solid, so we don't have any liquid superconductors. So there is no analogy to this that we can really create in a lab on Earth. Then on top of that soup of neutrons, protons, and electrons, we have the crust. So we have a solid region, so very broadly the structure that the Earth has. We have this solid crust, which is a little bit elastic. I'll come back to what I mean by that in a minute. And microscopically, what that is, it's a crystalline lattice of neutron-rich ions with electrons zipping through the crystalline structure. And then, as I said, the exterior is what produces the emission we see. So there you have these magnetic field lines that are sketched there. You have charges being accelerated along magnetic field lines, and those produce the emission that we see. And as I said, we don't know the details of radio emission, but we know that, well, we clearly see radio emission. We also know that you need quite particular conditions for radio emission. If you don't have those, the radio emission turns off, and that'll become important later in this talk. Okay, so that's radio pulsars. So if you're feeling shortchanged that the title is magnetars, so I'm now on to magnetars. So for those, so we discovered neutron stars in 1967. We found new neutron stars year after year, all in the form of radio pulsars. Then in the early 90s, and this wasn't really a discovery, this was Duncan and Thompson were a pair of essentially theoreticians who realized that some objects that we were already observing could be a manifestation of a new kind of neutron star. So in particular, there was a kind of an object called an anomalous X-ray pulsar, which is emitted in X-rays rather than radio. And there was another class of object called the soft gamma repeaters, which had a quiescent sort of low-level gamma ray emission and characterized also by some bursts. And so that the origin, the sort of central engine that was powering these two classes of object was not clear. Duncan and Thompson, in 3 papers, one of which, the 1992 one, was quite short, and then the 1995 and 1996 ones are monumental papers that really sketch out all the details of their idea, because in a sense it was controversial, said that these new classes of object, the anomalous X-ray pulsars and the soft gamma repeaters, could be a new class of neutron star, but the magnetic fields of those neutron stars would have to be a factor of 1,000 stronger than we've seen from radio pulsars. So at that point, this was really controversial. The radio pulsars we had, now we have a much wider range of observed magnetic field strengths. But at that point, the radio pulsars had there was a fairly clear upper limit, and it was well below this kind of magnetic field strengths that Duncan and Thompson were proposing. So this was initially controversial, and I think it was really about although the idea came from the early 90s and even the late 80s, it was probably the early 2000s where this became conventional astrophysics, if you like. So the idea, I won't give you the 40-page version of the idea, but the idea of this is that you have a different way of powering the emission than from radio pulsars. So for radio pulsars, you have this a magnetic field and you have a rotation, and together those two, in a way we don't fully understand, produce the radio emission. The idea of let me just see, is there a question in the chat here? I'm not sure I can't actually click on things in full screen, so.
Question is from David. He's saying, are the X-rays and gamma rays non-thermal in origin?
Okay, so there's two pieces. There's a sort of a thermal quiescent piece to this. It depends on the source, but there's typically a thermal nature quiescent piece, which probably comes from lower down in the crust or lower down in the corona. And then there's, on top of that, depending on the source, there might be these so I'll describe the detail in a minute, these high energy bursts and flares. So that the emissions probably from, depending on which particular bit of the emission, it's probably from different regions of the star, but there is a thermal piece. So the broad picture of how Duncan and Thompson believed a magnetar worked, and then this is I think none of this is controversial anymore, is that crust of the neutron star is a huge hidden reservoir of energy. So over time, like any elastic medium, you can build up stresses, and as you build up stresses, you're essentially storing elastic energy ready to be released if you can find a way of releasing that. And the reason why the crust is becoming stressed over time is because of the magnetic field that threads the crust, which, remember, is supposed to be a lot stronger than for radio pulsars. This evolves over time, and that builds up stresses locally in the crust. Eventually, the crust gets to a point where it can't take any more stress, and like any other elastic medium, it has to fail in one way or another. So break, in quote marks. So then when it breaks, that's sort of sketched in this diagram at the top. When it breaks, the magnetic field lines, which are essentially, they have foot points in the crust. So they start in the crust and then they move out into the magnetosphere, into this exterior region. When the crust breaks, it displaces those field lines, the foot points of the field lines, and it implants a twist in them, a bit like a twist in the solar corona. Once it's twisted, that it excites, it rips charges off the surface, and it sets up a kind of a steady state coronal loop where you have this twisted region of magnetic field populated by charges. So now you've taken the energy which was hidden in the crust in form of stresses, and now you've got it out to the corona. Then if you have some magnetic reconnection, some over twisting of that loop, you can then get a release of energy. So, and then there's a lot of detail about how the exact emission mechanism, but broadly speaking, that energy is what we then see as X-ray or gamma ray bursts. But like I said, to do this, you need magnetic fields which were a minimum of about a factor of 100 stronger than any we'd seen from radio pulsars at that stage. Okay, I showed a mysterious plot in the previous slide and didn't explain what it was, other than I put it on the magnetar slide. So let me talk you through what that is. So this is the most dramatic magnetar phenomenon, and arguably one of the most dramatic astronomical phenomena in any context. So this is a giant flare. So this is a magnetar giant gamma ray flare. And these are among the brightest events that we see anywhere in the universe. Not as quite as bright as supernovae, but there aren't many other things which are as bright as these. So you have a release of 10 to the 45 or 10 to the 46 ergs of energy. Sorry, we use these antiquated CGS units in astrophysics rather than, I think you have to divide by, I can't remember how many to get to joules, maybe by 10 to the 7, but I've forgotten now. I would have converted if I thought about it. But anyway, they're among the brightest astronomical events. And what we see is an initial gamma ray flash, so with an extremely short rise time of all of milliseconds, and then a decaying X-ray tail. So you see the initial flash there in that plot at a time of about 20 seconds or something. So then you have these huge photon counts. And actually at that point, the detectors that were on satellites that caught this event were actually saturated. So we didn't really see the top of the peak. It was such an enormous blast of radiation, it saturated all our detectors. Then after that, you have this gradual decaying X-ray tail. And the oscillations you can see in that are actually the stellar rotation period. So there's some sort of a fireball which is anchored onto one side of the magnetar, and that rotates around at the rotation period of a magnetar, which is slow compared with radio pulsars. In the case of this one, I think it's 8 seconds. And so that's what that modulation is, that those oscillations are as you see the fireball passing by the line of sight of the Earth. So as I said, you have a very bright initial rise, and then a decay over hundreds of seconds. And the fact that these gamma ray flares start so abruptly points to an event, something like a coronal mass ejection, which we actually see from the sun. So you can imagine that plot on that it's actually a photo on the bottom. Something like that is happening in magnetars, which we see as then this gamma ray flash. So initially, right before that giant flare, that energy was stored in the corona. Before it was there was this reconnection, and then we saw it. But the corona is not a good long-term energy reservoir. Energy dissipates quite quickly from there. You can't just keep it long-term hovering outside the star. So that's why before it was in the corona, that's why we think it was straight before that, it was in the crust in the form of elastic stresses. So, okay, these are the most dramatic events. Unfortunately, we've only seen 3 of them locally. So 2 within the Milky Way and 1 within, I think, the Small Magellanic Cloud. Very recently, in the last couple of years, one class of GRBs, of gamma ray bursts, short gamma ray bursts, have been linked convincingly to being magnetar giant flares, but from magnetars outside our galaxy. So in that case, you don't quite see all the information that's in that top plot with the flash and that long decaying X-ray tail, because the decaying X-ray tail bit would be too faint outside the galaxy. But so we have 3 we've seen close by, and then some that we sort of half see from well outside the galaxy. The good news is that this is really in the last couple of years. So there's hopes of getting far better statistics for how frequent magnetar giant flares are now that we've made this connection. Okay, so this is the most dramatic things that magnetars have done, but only 3 of the magnetars that we know have made a giant flare, and each one's only done 1, so that those 3 flares are each from different sources. Something that's much more frequent in magnetars is smaller bursts, and those smaller bursts have typical energies, so 10 to the 39 ergs, even lower in some cases. It's a bit instrument dependent for now. But typically the short bursts have an energy of about 10 to the 39 to 10 to the 41 ergs. So this is a factor of about 1 million weaker than the giant flares. And then in some cases up to about 10 to the 43 ergs for so-called intermediate events. So this plot, which is from a paper from last year, so this shows a burst forest in a sense. So you can see a number of short bursts, and then at around 300, just after 380 seconds, you can see that more prolonged event, whatever you want to call it. So we have quite a range. When you go to the smaller energy range, we have far better statistics for how frequently these bursts come from magnetars. And they appear to be localized. So it appears that it's not a kind of isotropic emission of energy from the magnetar surface. It appears that in the case of any particular given burst, there's a small active region of the neutron star surface, of the magnetar surface, where that burst is coming from. So that's interesting. Another thing that's interesting is that the statistics for these events, so basically how many events you have for a given energy range, so you have lots for the weaker events and then fewer for the larger events, those statistics look a lot like those of earthquakes. So again, luckily we have fewer large earthquakes than small earthquakes, but the similarity in the statistics already 20 years ago was making people think that there's some analogy in the mechanism between the emission of these bursts and what's driving the emission of these bursts and earthquakes. And that again makes sense if you think that this is a process that's driven by bits of the neutron star crust failing. But because of the energy range and because the energies are fairly small, and because these bursts seem to come from local active regions, it doesn't look like the whole crust breaks in one go. It looks like individual patches of it break for individual bursts. So that's the kind of sketch without really saying what the crust is doing and just assuming that the crust, one way or another, behaves in the way we want it to. How does the crust actually break? That's then a much harder question to answer, because then you go from this kind of sketch of how this process might work into really trying to do the nitty-gritty of simulating the failure of a neutron star crust. And this is a real challenge, and we're really, I think, only at the start of understanding the physics of how a neutron star crust can break, if you like. So what does a neutron star crust look like locally? So I said before, there's a crystalline lattice of neutron-rich ions. It actually forms, we think it's probably a body-centered cubic, so like this sketch on the left there. And it's the strongest material in the universe. In general, because neutron stars are so compact and at such high densities, that's essentially why they're the record holders for everything, for the strongest magnetic fields, for the strongest materials, and all of that. Everything is kind of extreme in the context of a neutron star. But even though it's the strongest material in the universe, like any other material, it has a point at which it will break under too much stress. Or to be more precise, it has an elastic yield stress. So if you take an elastic band and you start to stretch it for a bit, and then release it, it will go back to its original length. If you stretch it a bit further, it doesn't quite go back. It will stay kind of stretched. And if you stretch it too much, the thing will actually snap. So every material has a range of stresses for which its response is elastic. So you put the stress on the material, it deforms in some way, and then if you can take the stress away again, the material will go back to where it was to start with, to its relaxed state. But then if you keep adding more and more stress, at some point you get to a yield stress. So you get to a point of no return, where the response to adding more stress to the material is that the material breaks in some way, it yields in some way, it deforms in some way. And when we say break is not a good word really, because when we think about breaking, we think of brittle fractures. If you drop a glass or something. Because the neutron star crust is at extremely high pressure, brittle fractures are actually energetically disfavored. So to make a fracture, what really happens locally is you have a small void in your crystalline structure of your solid, and that void propagates through the crystal. And when it's completed propagating through the crystal, the material breaks. But under the huge pressures in the neutron star crust, those voids can't really form to start with. So you can't have a brittle, probably. We're starting to get into hypothetical. This is all a bit hypothetical so far, but there's no obvious way that you could form that void and therefore have a kind of brittle response to a very high stress. So instead, the only other way that it can respond to stress, which is higher than the yield stress of the crust, is a plastic deformation or flow. So the more, as you add more stress to it, the crystalline lattice is just distorted. The ions dislocate one from another, and on a large scale, you have this kind of flow. The state of the art for now is, but that this flow is a kind of a large macroscopic thing. This is not something that we'd like to understand how this happens on large scales, not on the scales of individual ions in the crystal. For now, the best we can do is those microscopic scales. So there are what's called molecular dynamics simulations, where people have built essentially a small cube, a small microscopic cube of neutron star crust, if you like, with a computer simulation, and put a shearing force at the top and the bottom of that little cube of crust to see how the material responds. So on a local scale, but this is a very, very local scale. On that very local scale, we have some kind of simulations for what happens. And it looks like basically the crust withstands an awful lot of stress, but then when it does break, it all breaks at once, essentially. This plastic flow affects the whole crystal in one go. So that's a problem on large scales. On large scales, that can't happen. If that were to happen on large scales, that would mean every time you got too much stress built up, even microscopic in a neutron star crust, that failure, that break, if you like, would sweep across the entire crust. So that's firstly not plausible, and secondly, it doesn't fit in with our observations of these many smaller and then less frequent larger bursts. So one way or another, there has to be some sort of scale for how this material yields. So then in a bit more detail, why does the crust break? So I gave a one-liner saying that you have a buildup of magnetic stresses, but that we can actually simulate. Again, this is a local simulation. So what I'm showing you here is, again, this is kind of a little cube of neutron star crust. The vertical axis is depth. So the top is higher up in the crust, and then the bottom is deeper into the crust. And then the other scale, the horizontal scale, is just, well, any horizontal direction in the crust, basically. So we have equations for how the magnetic field should evolve in a neutron star crust. So we can solve those on a computer with a numerical code, and we can see what happens. So if we start with this simple two-loop form of magnetic field on the left, so these black lines are magnetic field lines which are in the plane of the screen. And then the color scale in the middle is going to be magnetic field that builds up over time, that points into and out of the screen. So the magnetic field points in all three directions, but I obviously can't show the third dimension on a flat screen. So that's why it's shown with the color scale. So what happens? You start with this setup on the left. I mean, you can choose whatever setup you like, but this is just for illustrative purposes. And then you evolve the magnetic field over time. And after 500 years, you produce the plot in the middle. So now you can see those two large loops of magnetic field lines from the left-hand plot. They've become squashed and distorted into the middle plot. You can see kind of kinks in the bottom of the middle plot as well. And then you can see these. To start with, there was no magnetic field into and out of the board, out of the screen. Now there's a strong magnetic field, parts of which point out of the screen towards you, so the bits that are color-coded red, and then other parts point into the screen, so away from you, and those bits are coded blue. So this complex, small-scale structure is developed over time. But meanwhile, whilst that structure has been developing, because the magnetic field has changed from its original structure, that's caused the crust to become stressed. And on the right, I show the stress pattern that builds up. Whilst the magnetic field is evolving in that way, this is the stresses that are building up in this little patch of crust. And in particular, when that color scale, it's actually blocked on, because I'm in full screen, it's blocked here. I've got pictures instead, but I think you can see the color scale on the right-hand side. This is in units of yield stress. So it's the stress divided by the yield stress. So whenever that number is bigger than 1, you're above the yield stress and the crust should break. So you can see basically all of those darker red regions are regions where the crust is so stressed it wants to break in some way. But this is not yet in these equations that we're solving here. So for now, we're just solving the magnetic field on its own and forgetting about the fact the crust should break. We can kind of play these theoretical games because we don't really have a piece of crust. We're just looking at only the magnetic field evolution for now. But given that we know that the magnetic field should have broken the crust before we even get to that middle plot, we can then add in the effect of the plastic flow that will develop once you get beyond the yield stress. So I think this video is going to play automatic when I go to the next slide. Or not yet. Okay. So I'm going to compare, firstly, what the magnetic field evolution looks like without taking into account the fact the crust fails and undergoes this plastic flow. And then in the B video, you'll see what happens when there is plastic flow. So I'll play them a couple of times. So we start with 2 big loops of magnetic field, as before. So you can see over time, these sort of sharp features appearing in the magnetic field lines, and you get these strong regions with magnetic field pointing towards you and away from you in the blue and the red. So I'll play that again. And those 2 original loops have merged into one. So I'll play that once more. So this is without plastic flow. Now when I put plastic flow in, because you would expect plastic flow to kind of counteract the buildup of stresses. So you'd expect the evolution to be a bit smoother. The plastic flow kind of acts against this evolution that you've seen on the left. So now let's see the same evolution, but now with plastic flow. So everything is much slower. The evolution takes much longer to get away from that initial condition of the 2 loops. And in fact, those 2 loops are still sort of preserved there. And then the color scale showing the field coming towards you and away from you, that magnetic field structure is now much smoother than it was with in the case where that plastic flow was neglected. So these are some simulations I did with a colleague in Greece, Kostas Woodward-Gatos. And these are the first simulations showing the effect of that magnetic field evolution when you take into account the fact that the crust will flow plastically. So some evolution a bit like what I just showed you there on the right-hand movie just now. Some evolution like that will be going on locally in different bits of the crust. And I say locally because we know, I haven't shown you any kind of 3D simulations here, but we know that the stresses that build up in the crust, it's not that the whole crust becomes stressed all at once. The stresses tend to form a characteristic pattern that are about of high sort of stress patches, which are about roughly 1 kilometer squared on the neutron star surface. So remember, the radius of the neutron star is about 12 kilometers. So one kilometer squared is a moderate fraction, a moderate sort of fraction of the crust. It's not quite as big as what I've sketched here, because this is just for illustrative purposes, but it's a reasonable sized patch of crust. And the interesting thing is that with a patch, if you look at the failure of a patch of crust of about 1 kilometer squared, the amount of energy you expect to get out, just on theoretical grounds, is about 10 to the 39, 10 to the 40 ergs, which is, if you remember from before, that's about the characteristic lower limit on the sizes of bursts that we see. So there's hints both from the theory and from the observations. I have to wait for these movies to play before I can go past this slide. But there's hints both from the theory and from the observations that for the smaller bursts, we're getting individual cells of the crust which are failing. Then when they fail, so you get a plastic flow. That plastic flow then twists those field lines which are anchored into the crust. So they start, before the crust fails, you get a little coronal loop like the one on the left there, where there's, you see the three kind of concentric blue circles. And then on the right, when the crust fails, you start to, you twist the foot points of that coronal loop, and you start to braid those field lines, and then you get a little coronal loop with charges. And so then you've got that energy from the crust out into the corona, and at that point then you can get your little X-ray burst. So that explains the smaller scale high energy bursts. Then in principle, the cells are sort of semi-autonomous, if you like, but they also communicate with one another. And under certain circumstances, one cell failing can trigger another cell to fail, and then you can get the kind of avalanche of failure that spreads across the crust. So in that case, then you can get, very rarely, but you can occasionally maybe get a giant flare, so one of those enormously energetic events. So basically, the whole of the high energy activity can be unified in a kind of single model of how the crust quakes, if you like. So that's the kind of the high energy story, and that was up until a few years ago. That was the characteristic of magnetars, this high energy bursting activity. Then the fast radio burst came along. Or rather, the high energy burst, the fast radio bursts, plural, did not come along. One came along. So one was discovered in 2007 by a team. The first author was Duncan Lorimer, so it's often nicknamed the Lorimer burst. So there was this bright, very brief radio burst discovered in the data with duration of about a millisecond. It looked like a real event. So in this frequency time plot that radio astronomers do, it has this characteristic kind of, the burst has this kind of characteristic path through that plot that astrophysical, so events from beyond the Earth itself, have. So that got published. There was a lot of, I mean, it was an enormous puzzle as to what this was, and this was in a sense one of the first brand new astronomical phenomena for years, really. But there was a lot of, and there was several teams who were, of course, trying to look for other such fast radio bursts, and nothing was found for the first years. So there was a real puzzle about this one 2007 burst, about what its origin could be. And although it looked astrophysical, because people couldn't find a second such burst, there were doubts about this, about whether this really was a genuine phenomenon. And something that made those doubts worse was that around about the same time, people were discovering what were nicknamed peritons, and these were these were not astrophysical events. These were some kind of radio interference. It was a little blast of radio waves, and this was seen many times. So at the same time as you had this single, if you like, real fast radio burst, there are also radio things that looked a bit like radio bursts, but were clearly interference that were being detected. So that cast a bit of doubt on this one real burst. In the end, the mystery of the peritons was cleared up, but it was hungry astronomers at fault. So I think in particular, if you if you're microwaving your lunch at a radio telescope facility, so your mobile phones are turned off and everything else. But then if you get too hungry and you open the microwave door before the program is finished, that sets off a little blast of radio waves, which is detected as radio interference. So eventually the mystery of the peritons was solved. So that was, well, those were clearly not astrophysical events. But the mystery of the fast radio bursts was very much open. And for any new astrophysical phenomenon, theorists have enormous imagination, and a huge number of models were published in those first years. So really, I think of the order of hundreds. The one clear way to distinguish between the two classes of models was that most of those models were one-off models. So a chance event like an asteroid hitting a neutron star or something, or a neutron star in spiral. Once the two neutron stars have been spiraled, you form a black hole. Nothing else then can happen after that. So a lot of those models would just give you a single FRB and then nothing. So people were waiting to see if there would be a repeating FRB source, because if you start to get a repeater, then that really whittles down the number of viable models. Of course, eventually we did indeed get repeaters. So 9 years after the Lorimer burst was published, there was the discovery of the first FRB repeater. And at this point, this becomes a huge boost to models that propose that FRBs were of magnetar origin. Essentially, if you have a blast, an energetic blast of radiation, which is of short duration, you need to look out in the universe for some place where you have a huge reservoir of hidden energy that can be released episodically like that. And the most logical place to look then is the neutron star crust. By that point, the magnetar was conventional astrophysics, so it was the most logical. It was the most logical candidate for FRBs as well. Then finally, a couple of years ago, we actually saw an FRB from a magnetar. So from the galactic magnetar, SGR 1935, in between a period of high energy bursting, we also saw an FRB. So that made a lot of sense in a way. But there's a big question here, which is that the conditions that you need to produce high energy emission from your magnetosphere, from your corona, are very different from the conditions you need to produce radio emission. And we've seen from neutron stars before that the radio emission in some cases has turned off and you get a high energy burst, and then the radio emission turns back on. So this was a bit of a puzzle. It looked like magnetars could power all of both the high energy bursts and the fast radio bursts, but you need different magnetospheric conditions. And in particular, for radio emission, you need a region of a charge-starved region. So you need a very limited number of charges. So that sounds like a contradiction if you think globally, if you imagine the corona is one big entity. But if it looks like this sketch here, where you have individual coronal loops, some of which are twisted, some of which aren't, then that makes more sense. So now in this picture, you can have from some region of the magnetar crust, you can have a fast radio burst. From other regions of the crust, you can have high energy bursts, and those can be essentially almost simultaneous. So I think this is my penultimate slide, unless I've forgotten that one. So I want to just talk for a minute about a particularly interesting source that I got involved in the modeling of from earlier this year. Well, actually, we started about 2 years ago, but it got published this year. So this is SGR 1830. And so it was seen in its well, we first found it when it let off a bunch of small X-ray bursts. And after that initial sort of period of bursting, it continued to emit bursts. And then as well as the bursting, it had this complex X-ray profile, which you can see here on the left. So this is in units of, so it's phase on the x-axis. So over the period of one rotational period, you go, well, in the way it's plotted there, your X-ray emission reduces, and then it increases to this peak at a phase of about 0.9 on the x-axis, and then it drops again. And this is 2 rotational phases, which is why there's 2 peaks. So you can just look at the first peak. So the amazing thing about this source, though, is it's not a single peak, which is what we've been accustomed to seeing from the steady high energy emission from magnetars. There's this complex 3-peaked profile. So this is really interesting. But what's even more interesting is that over time, that profile is evolving. So that blue line at the top is the profile integrated from day 0 to 1. So day 0 is, the discovery day. And then as you go down from the blue down through to the green, then those numbers show the days that are folded together to make that profile. So the second one is then days 1 to 3, and then days 3 to 7. You get down to days 34 to 37, then the sun got in the way. So then there was this period where we couldn't observe it because it was too close to the sun. We were able then to see it once again from day 123, again relative to that discovery day. So it turned back on. We were able to see it again at 123, and that's these green profiles at the bottom. So those peaks are evolving over time, and they're also merging. So if you can take the 3 peaks from the centroids of those 3 peaks from day 0, and you can draw these. We drew these vertical lines in here. So the black one, the 2 black ones, and the grey one at the centroid of where the peak is to start with. And then we can see visually first from the left what happens to those peaks over time. So you can see the right-hand peak doesn't move so much. You can see it moves a bit to the right. The middle peak moves a bit to the left, and then the left-hand peak, sorry, the middle peak moves a bit to the right, and the left-hand peak moves a bit to the right as well. So those, you can see visually that those are merging. And then you can actually plot the centroids of those peaks over time. So this is showing, as a function of where you are in that rotational phase, what the peaks are doing. So you can see there's this gradual trend for those 3 peaks merging over time. And that was really interesting for someone who's interested in studying the crust, because this looks like the first essentially direct evidence of crustal motion in action. So those 3 peaks, it looks like they're different bits of a local active region on the crust where the peaks are being moved in over time. And the only thing and the time scale on which they're moving in and merging, which is of order a month or so, there aren't many processes that we would expect to be, there are some processes we would expect to be much, much slower, of order years, and there are some processes we would expect to take of order seconds. But that period in that characteristic timescale of a month or so looks a lot like a plastic flow of the crust. There's basically nothing else, at least that we can think of, in that time range. So this may be really the first direct evidence watching the crust moving, the crust in action. So yeah, I want to finish with that. So yeah, in summary, magnetars are powered by the huge amount of energy they have stored in their crusts. And the energy stays there until the stresses get too large, and then some of it is released. The details of how that works are still poorly understood. Even this basic modeling, like this microscopic simulation of a little cube of crust failing, this is still, this is state of the art, but it's still a long way from a real magnetar. But we're seeing more and more manifestations of normal neutron stars, more and more different kinds of magnetar activity. And I think over the next few years, we're really going to, together with improved theoretical modeling, we're really going to start to build a better picture of just how, in a quantitative way, the crust really powers all that activity. So I think I've just about filled a whole hour, which is a bit more than I intended to, but thanks for your attention. And if you've got any questions, I'd be happy to take them.
Yeah, thank you very much, Sam. Absolutely fascinating. Yeah, but there are some questions. I'm looking at one in the chat from Simon Street. He says, can you tell anything from how the crust behaves from one magnetar to another? For example, identifying different neutron-rich ions.
So in a sense, yes. The problem is that there's a lot of there's enough aspects of the modeling which are not under control that it makes it hard to really pin things down. Actually, the structure of the crust and the different neutron-rich ions, that we know reasonably well, and that's because the crust is still a little bit below nuclear density. The ions in a neutron star crust are much more neutron-rich than on Earth. On Earth, all elements are, all isotopes of an element have roughly equal neutrons and protons. And the ones that have a lot more neutrons than protons are unstable. So, but broadly speaking, from nuclear physics theory and from experiments, we have a reasonably good understanding of the structure of the crust. So as you descend further into the crust, how the ions change. The thing that we really probe with magnetar activity is, I would say, is the material properties of the crust. So just as if you're an engineer and you want to know how strong your piece of steel is or whatever, you can go into a lab and you can stress that and you can see where it fails and how it fails. We can't do that with neutron star crust material, and we never will be able to, and we can't really simulate it. But that's the thing that we really learned in an indirect way from different magnetars, maybe if they seem to be at different temperatures or different ages, we start to get indirect hints of how that crustal failure works. But it is an indirect tool. It's not the same as going into a lab. You have to really just use that very indirect information that the magnetar gives you.
Peter East is asking, are there many magnetars that you can study in this way?
And I guess that's sort of the answer is similar to the last one, in the sense that when a magnetar deigns to do something interesting for us, we celebrate it, and two of those three giant flares came in relatively quick succession. So one was, I think, 5 or 6 years after the other one, but the last one was in 2004, and we've gone for 18 years now, and we still don't have another one, which is is frustrating. So for some of those things, we're waiting and hoping, and that's the case for a lot of things in astrophysics. You wait and hope for something to come along to give you some more information, but you make do with what you've got, right? So that there are things that we can do. So although small bursts in themselves are maybe not, an individual small burst is maybe not that interesting, the statistics that you get from a couple of decades of small bursts from one source and from another source, and comparing those, you can start to infer some interesting general properties for what's driving those bursts. Just like so for example, with this comparison with earthquakes, you can infer some things about the process that's driving the bursts. But so in a sense, any magnetar that undergoes bursting activity of some kind is an ingredient in this study. But yeah, we have to take what we're given, in a sense.
How many unique magnetars have been observed in this way? I don't have a feel for the numbers.
It's of the order tens, and not many tens. I think it's roughly. Yes, it's not the question to ask a theorist, and the answer is not as clear as it used to be. So maybe roughly 20 to 30, but it's also a bit. The definition of magnetar is a bit of a loose one. At the point of the early 90s and even up to about 2000, maybe 2010, there was a fairly clear distinction. Something is a radio pulsar and it pulses in radio, or something is a magnetar. And then we started to see more objects where a radio pulsar would turn off, the radio would turn off, and then we saw a magnetar-like burst, and then the radio would turn back on. So magnetars are not really a different breed altogether. All of these things, all of these objects are neutron stars. And just depending on details like their age, their external magnetic field, how stressed their crust is, we might see them behaving like magnetars or behaving like radio pulsars. So it's not that easy to categorize them, but in a sense, classical magnetars that do classic bursting and nothing else, I think it's of order low tens anyway.
Norman Gray asks, the SGR 1830 time graph seems to show a convergence at approximately 120 days. Is that right? Is that a correct interpretation? Yeah, there's a broad convergence. So that there's a couple of problems. One is that, so like I said, the sun got in the way for about 3 months or something, and by the time the sun was out of the way again, that pulse profile was a lot simpler. But also the magnetar was just dimmer in general. So it's not. I'm not sure by that stage how much it's that the peaks have merged and how much it's that, because just the overall brightness of the source is lower, we don't distinguish those features as clearly. And Andrew Thomas is asking, can the crust slip over the core, or is it solidly locked, to the boundary?
That's not completely clear. There are mechanisms that could cause there are reasons why the core could be involved in driving this motion. In general, Occam's razor says we can explain all the activity we've seen with just the crust being involved. The core is in some sense, because it's superconducting and superfluid, in some sense it's sort of inert and doesn't as willingly participate in all of this. But also, for now, all of the activity that we've seen is consistent with just the crust being involved alone. So given how many other uncertainties there are, although the core could be involved in some way, it's not worth trying to put that into the modeling as well, because it doesn't really sort of gain us anything. In principle, it could be.
And is the rotational axis of the magnetar preserved from its parent?
That's really unknown, because when we say the magnetic axis, firstly, it's assuming the magnetic field has a kind of symmetry about some axis. And secondly, that axis probably, around the birth of the magnetar, the magnetic field is amplified and wound up around the rotational axis and then evolves away from that over time. So the axis, well, the rotational axis itself, probably in a sense where it points in the sky, probably doesn't. I'm trying to think. It wouldn't necessarily change, but well, no, that depends on. There's a lot of messy birth physics, like it happens in the supernova, and then where you amplify the magnetar's magnetic field shortly after birth, and that can change a lot, to be honest. So there's not that much you can necessarily safely infer from a magnetar about what its progenitor star looked like.
There's a question from Wolfgang, and Wolfgang's done a lot of observational work on fast radio bursts. And Wolfgang, I'm going to ask you to pose your question.
Yes, I was wondering, the majority of the magnetars known, they emit in the X-ray, they're known to emit in the X-ray, and only a few, something like a handful, are known to have activity in the radio regime. What do you think are the ingredients that make a magnetar radioactive? I'm particularly interested in magnetars like the XCE 1810, which has, I think, been the first to be detected in radio, which then became silent and then became radioactive again in 2018 and has been active ever since. So what makes them, what is the ingredient that is needed to make them active in the radio regime?
Okay, so yeah, thanks for the question. So yeah, there are, I think there are a total of now 6 radio loud magnetars. In a sense, giving a detailed answer is hampered by the fact that we don't understand the details of pulsar radio emission, just conventional pulsar radio emission. But broadly speaking, you need some region of the magnetosphere where you have a very low charge density, that the charges in a sense can't carry all the electric current. You build up a strong electric field, and by some process or another, that leads, you accelerate charges and you get radio emission. So it's difficult to give a clear answer to that, because there's also, for example, there are other just conventional pulsars that turn off and turn back on, or go from one spin down state to another. It looks like there is some kind of intrinsic, for example, a couple of different magnetospheric states that a neutron star might switch between, but we don't really know why it would switch between one another. Sometimes they do it rather relatively regularly, and sometimes it's a kind of a one-off thing. But broadly speaking, you need an emitting region where you have, which is charge starved to get radio emission. But then the details of why an object would go from being radio loud to radio quiet, or just turn off completely, or go from radio to high energy emission. The picture I have in my head is that there is probably something that drives the switching of the star between one of maybe 2 different possible magnetospheric states, but it is not really obvious, I think, to any of us why there are those 2 states, if that makes sense.
And a question from Aphrodite, would a larger mass magnetar behave differently from a lower mass magnetar?
In principle, maybe, but the difference between the masses would probably be less significant than the difference in the differences due to the different magnetic fields that the 2. So depending on how old the magnetar is, the magnetic field strength in the crust might be a bit stronger or a bit weaker. For a larger mass magnetar, so the crust would be sort of around, yeah, I don't want to say the wrong way around, but the crusts would be of different thickness. I think that, yeah, I'm not going to say which is the thicker and then get it wrong, because I'm confusing myself. But if the crust is smaller, in principle, the energy reservoir might be smaller as well. Basically, the thicker the crust is, the more room you've got to store elastic energy. But it's probably not, given how sort of crude our modeling is and how limited our observations are for now, that's not the kind of the main factor that dictates how a magnetar behaves, I think.
And Simon Street is commenting, the timing glitches seen in normal pulsars, he understands, are due to interactions between its crust and its core. Is that correct?
So most of them we think essentially just the crust that's involved. So the crust, I didn't say in detail. Let me just actually go back to the slide. So I mentioned that there are these neutron-rich ions. I mentioned there are electrons zipping through them. I didn't actually mention that as you go into the inner half of the crust, that neutron, you have neutron superfluid in the core. There's also neutron superfluid in the inner crust, so that the ions become richer and richer in neutrons, and some of the neutrons, the expression is that they drip out of the nuclei and they become this free fluid. But because it's a superfluid, it doesn't, in a sense, it doesn't interact very strongly with the ions. So the crust spins down over time, so it's rotating more slowly, but the superfluid for a while doesn't follow the crust. The superfluid is still rotating more quickly. So there's a lag in the rotation rates. Eventually, when the lag gets too big, the superfluid briefly recouples with the crust, and that's when we see a glitch. So for most glitches, it's just the crust that's involved, and it's just an interaction between the crustal lattice and the superfluid in the crust. It might be that the core might have to be involved for some of the larger glitches, but yeah, that's a bit of a different kettle of fish.
And the last question in the chat, Norman is asking, what's the theory over the merger of two magnetars?
That's quite an open-ended question. So in general, two magnetars merging is intrinsically going to be less frequent than two normal neutron stars, if you like, merging. And that's because two things. Firstly, we think magnetars are about 10% of the population of neutron stars. And secondly, magnetar is not a label that the star is born with and lives all its life with. Magnetar is a name for a neutron star that undergoes this high energy bursting. But over time, as it's sort of releasing, over time the magnetic field decays, the crust de-stresses gradually through these bursts. By the time a neutron star has lived long enough that it's found a companion to form a binary orbit with and then eventually merge, which is a process that takes millions and millions of years, by that point, most of the time, it would be rare for one of those two objects to still be what we would call, a magnetar in a sense. If in principle, if you got lucky and there were you did have two magnetars merging, I think these things have been, people can do computer simulations of this kind of setup. I think the biggest thing is we get a large gamma ray burst at the point where they merged and formed a black hole. That's the sort of short answer. There's two different answers. One is a sort of population dynamics answer, and one is just the details of if those two magnetars get lucky and are in a closed binary orbit. I think yeah, the main, it can be simulated numerically, this setup, and I think the main result would be you just get some really powerful short gamma ray burst, for example, and then the result would be a black hole. So then after that you get nothing.
Well, that concludes all the questions, great questions in the chat. Before we finish, we've got a couple of minutes. Does anybody have a question they're burning to ask in real time, as it were?
Maybe I can ask a direct question. We've seen the changes essentially in the profile of this one magnetar, where you have shown the X-ray emission, which has changed this profile over time. Yeah, that's the one. What I find interesting is that we see essentially something similar in the radio regime on XCE 1810. If we look at the evolution ever since it's best become radio bright, there was a relatively strong variation in the profile, with evolving a secondary peak, and then it sort of got less radio loud, but was still visible. and then for a long time it was just a single pulse. And what we are seeing right now recently is again the evolution of another interpulse. So there's a great variety. You have attributed that to the changes in the crust for the X-ray regime. Would you also say that's essentially the same effect that we are seeing in the radio?
So if you were talking about a normal radio pulsar, I would relatively confidently say no, because we think that the stresses are typically lower in those crusts, and although there was this one pulsar J1119 which had a glitch, and then at the same time there was a high energy burst, in general we don't see the same evidence that the crusts of radio pulsars are active in the sense of magnetars. But because you're talking about a magnetar, and because it's not completely clear that the mechanism for radio emission from magnetars is really exactly the same as for radio. So for radiolab magnetars, it's not necessarily exactly the same as for radio pulsars. It's a bit harder to be confident, I would say. So did you say there is this evolution of the pulse profile over?
Yeah, the time frames are in a couple of weeks or months. So we're talking about, well, we've been observing this magnetar since it became radio bright again in end of 2018, December of 2018. And essentially we've been following it with relatively high cadence over the time until now. There was a time in between when it was the emission was too low for us to be detectable with our 25-meter dish, but now it's fairly bright again. And we're seeing all sorts of evolutions in it. In a nutshell, in the beginning, it was behaving very much like a pulsar. We saw evolution of the profile, and we saw every now and then, in the terms of, let's say, one every couple of days of a very bright single pulse, which was detectable as a single pulse. Then there was a period last year, was last year, I think so, or maybe the year before, when there were a couple of months, I would say, when there was extreme high activity of single pulses, which would qualify, if it were a pulsar, which would qualify as giant pulses. Okay. There were in 100 of Jansky's peak flux. And those were like 100 of these per hour. And this has died down again, and we're seeing it now coming up again. So there's extreme variability in the radio emission over over this time span. And the only thing that reminded me of, I saw this evolution of the profile in the X-ray that you have shown on your slide, and we're seeing essentially similar things in the radio regime. Okay. So essentially, it's this guy does all sorts of things and changes every couple of weeks, and it's fun observing it, but it's really hard to tell what is the cause of it.
Yeah, no, it's a really interesting source. I didn't, other than knowing it was radio loud, I didn't really know any of the details of what its radio emission was doing. That is really interesting. I think it's not impossible that there's something similar at work. I think it's so hard with these things to pin down the origin of what's driving the emission. Of what's driving, for example, changes in the emission. But one thing that is, I would say, secure, and this is what made me believe that we're probably seeing crustal motion in this slide I have here, is that it's this timescale argument that if you say there's an evolution over a certain timescale, you have to ask, well, do I know any physical mechanisms that act over this timescale? And that can be difficult. So there are. In general, it's easy to find mechanisms that cause changes over milliseconds, and it's easy to find mechanisms that cause changes over decades. But changes that happen over months are not necessarily that easy to pin down. So it's intriguing. No, thanks for alerting me to this, because I wasn't aware that there was anything remotely similar from a radio magnetar. It's probably worth looking at this if I ever get some free time in more detail. Thanks.
Okay. Sam, thank you so much. You engaged your audience fantastically this evening. And again, as I've noted with other of our speakers, that we'll have to get you back again in a couple of years' time, when maybe there'll be answers to all those open questions where the observations and the models don't give us all the answers that we're looking for. So Sam, thank you so much for giving up your time at a very busy part of the academic year. It is appreciated, and yeah, we do applaud you. And yeah, if we were in a theatre, I'm sure we'd give you a standing ovation. So good night, Sam, and have a great term. And we'll see you again one day, I'm sure. Good night and enjoy your weekend, everybody.
Okay, thank you all very much for listening and for all the interesting questions. I really enjoyed that. Thank you.
Thank you very much.
Okay, thanks.
Good night.
Good night.